Let's continue to talk more about the inner product space. In the previous video, we have introduced the concept of a mapping that is called inner product. It's a function that maps from two arguments in the same vector space to a real number that has three properties. Um, in this video, we would like to express a benefit of having an inner product structure defined on your vector space, because whenever you have inner product, and if you take an inner product of x with itself and then take the square root, if we construct the quantity in this way, we can show that uh, the result that we got is a norm. And it is called an induced norm according to such inner product you choose. For example, in the vector space of Rn, if you define the inner product with x transpose y or y transpose x, okay, if you have defined it in this way, we say that the induced norm that is induced from this inner product is going to be x transpose x. And that is the typical two norm, the conventional two norm that we already saw. Also, another example is the product, sorry, the space of m by n matrices. We have we have seen that an inner product on this space uh, is the trace of y transpose x. Okay, induced norm that is induced, that is derived, that is a byproduct of this inner product is going to be the square root of inner product of x with itself. And this expression is nothing new again, because we already see that this is actually the Frobenius norm of a matrix. Okay, so this is the definition of induced norm. You can go on. For example, what about the set of continuous function where you define an inner product as um as the product of f and g, and then you integrate over the support of that continuous function. In that case, the induced norm with respect to this inner product is going to be the square root of integral from a to b ft squared dt. Okay, and for those who have studied the space of uh, Lebesgue integral, this is the L2 norm of a function. Okay, we're going to come back to this slide because we're going to show that the induced norm is always a norm. The first property is pretty obvious. The first property that is the homogeneous property, because it's quite obvious, because by the definition it's going to be square root of inner product between alpha x and alpha x, and you know that you can take the alpha x, the constant alpha here, and that's going to be absolute of alpha times root of x and x, and that is the absolute of alpha times the norm of x. So homogeneous property is satisfied. The positiveness property is quite obvious from the construction of the induced norm. It's just only the triangle inequality that is not obvious. But before going to do that, I would like to introduce the very well-known inequality that gives you a connection between inner product and its induced norm. Cauchy-Schwarz inequality is defined on any inner product space V. Suppose this is inner product that you use from that space. It just says that the magnitude or the absolute value of inner product between x and y is going to be less than the norm of x times norm of y. And that is not any norm. It is the norm that is induced from this inner product. Okay. Um, for example, if I first of all, if I pick to be Rn, pick V to be Rn, and I just use the conventional inner product as Y transpose X, this simply says um, the absolute value of Y transpose X is less than the two norm of X and Y. Because two norm of vector X and Y is the induced norm from this inner product. Okay. Or if I apply Cauchy-Schwarz on the space of rectangular matrices, if I use the conventional inner product again, this Cauchy-Schwarz inequality says that the absolute value of trace Y transpose X is going to be less than the Frobenius norm of X times Frobenius norm of Y. Because we just saw that the Frobenius norm is the induced norm from such inner product. Okay, let's see some example, maybe some non-trivial example of the Cauchy-Schwarz inequality. The first one is actually the triangle inequality. It's actually the property that we have to show if a norm is a norm. Like if you define a norm, one of the property that it has to satisfy is this one. So in this example, let me just show that if I use the two norm, for example, of Rn of vector u and v in Rn, why the triangle inequality is satisfied. So we can start with the square, okay, with the square thing. And because the norm square is inner product between u and v, all right? And you're going to get u transpose u plus v transpose v plus 2 times u transpose v, okay? So you got a factor of 2 because you're going to have u transpose v and v transpose u. And in the vector space Rn with a field of real number, I mean, u inner product with v and v inner product with u would be the same, would be symmetric. And now at this step, we can make an upper bound using Cauchy-Schwarz inequality because we apply it to this term with a factor of 2. And then we can see that the first term I'm going to rewrite again, that is going to be norm square of u plus norm square of v. Again, the reason why I can change d to the norm square, because now I'm using the induced norm of u, is the induced norm that is derived from this inner product. So let me put a little note here that now it is two norm. Okay. So after that, you can see that you can make a complete square. All right. That because this is the first one square, the second one square plus 2 times the first times the second. Okay, and that proves the triangle inequality. The next example is the following. What if this is some inequality that you need to show? So let's maybe you pause the video and think about it, and let's compare the answer. Okay. In this example, you will see that in order for you to derive, okay, so if we going to apply this Cauchy-Schwarz, to apply that probably is not straightforward because you have the sum square, the sum of the product and then square, right? So maybe you decompose xi to be ui vi root ui, and then you split y to be the square root ui. So you try to think of x and y so that the norm square of them gives you this one. All right. I figure out that the norm square of something, this is going to be the sum of u. So that's why I define y to be square root of u. So in this case, you're going to see that y transpose x, which is the sum of xi, yi, is going to be the sum of vi, ui, right? Now I can make squares. And then the norm square of x, that's going to be the sum of xi squared. That's going to be the sum of vi squared ui. And obviously the norm of y is going to be sum of ui. So you see that if you choose x and y in this way, this inequality just follows directly from the Cauchy-Schwarz inequality. Okay. The proof of the Cauchy-Schwarz inequality is the following. We can start with x plus alpha y. X plus alpha y. So alpha is any scalar number. X and y are two vectors. We know that the norm of some vector is always non-negative. And if we just expand this norm square by using the so we know that norm square of something, this is the induced norm from some inner product, right? So we're gonna write this as inner product between x plus alpha y with itself. And now you just expand this inner product. You're gonna get x and x. You're gonna get alpha square y and y. And then you're gonna get alpha y x and x with alpha y. All right. And now you make use of the property that is linear in the first argument. Okay. And and you can see that and use the symmetric property between these two guys, you get this. All right. So this quantity is always non-negative. Then for y that is non-zero, we'll come back again why it is quite general to assume this. So if y is non-zero, we can select alpha this way because the denominator now is always non-zero. But if we plug in this alpha to the expression, we would get something that is always non-negative, right? And I just plug in alpha to this term, so I'm gonna get this, right? And then the other term, I just plug in the other term, I'm gonna get negative 2 xy squared divided by this one. Sorry, this has to be square. So at the end, you get something that is this term with the coefficient negative 2. This is a positive 1, so it gives you negative 1. Okay. So once you got that, this quantity is always non-negative. And that just gives you the Cauchy-Schwarz inequality. Okay. So this is very general to assume that y that is non-zero, because if y one of them is 0, the Cauchy-Schwarz inequality would become very trivial. Okay. We can see that the Cauchy-Schwarz inequality becomes equality when x is a multiple of y. Is it obvious? It's obvious, right? Because the inner product between y and x would be just uh, cy and y, and that is the magnitude of c times norm of y squared. All right. And of course, on the right hand side, the norm of x would be absolute c norm of y. All right. So that's quite obvious. Mhm. Um, you can maybe take a look at the meaning of the inner product in the Rn space, because we all see that the inner product between x and y, right, is always less than this guy, because of the typical formula that you already know, that transpose x transpose y is going to be uh, x times y times cosine theta, where theta is an angle between x and y. Oh, no, let me show. Okay. This is from our prior information when we learn about vectors, right? Um, so we can generalize this concept. How about we using this cosine theta and define it, generalize it so that it can be a similarity index for any inner product. So if we define cosine similarity as inner product between x and y divided by x times norms of y, this is going to be the quantity between -1 and 1. It can be -1 when y is a negative, some negative number times the vector x. Okay. So cosine similarity has been used a lot in applications. It can be an index or matrix that tells relationship or similarity degree between two vectors in inner product space. Now let me give you example of inner product space of functions. Continuous function in the interval of 0 to 2 pi. I have a function sine x that is given by the blue curve, and I have two functions g and h that are cubic polynomial. They just differ by the coefficients. If you take a look at this graph, how can you tell similarity between f and g and f and h? Because this is like you cannot compare the whole curve, or you must aggregate all the points on the curve, and let's use some metric, some degree to actually see the similarity. So if we just apply the cosine similarity index that says cosine theta is inner product between y and x. In here, it's going to be just follow the notation. It's going to be f and g, and norm of f times norm of g. All right. So this is to measure between f and g, and to measure between f and h, you just use the same formula. So this is between f and g. F is sine x, gx, and this is norm of f, this is norm of g. If I just plug in the cubic polynomial there, I can compute this cosine theta. Okay. And what I show on this graph is some similar concept. But what happens if we just consider this graph as their discretized value? The whole curve is subsample at a set of points. So basically, we can keep the information of f by using array in Rn. So let's suppose the blue array is from f, the orange or the red array is from g. So so after I discretize my function, my vector is now a vector in Rn. If I want to tell the similarity in this discretized function, so I can use similarity index in the vector space of Rn. So I just use f there. Now this is going to be f in Rn. I take the usual inner product and divided by the two norm. Okay. Um, let's come back a little bit, all right? Because we We still have some information that I need to address. You see that the Cauchy-Schwarz inequality is very useful, but in order to apply that, let me just make a note again that this has to be the induced norm of of the inner product you choose here. When you work with Rn, you may have seen or similar results or uh, something that is very looks like Cauchy-Schwarz, but actually is not. That inequality says y transpose x is less than one norm of y less than infinity norm of x, or you may have seen uh, the other way around, the one norm of x times the infinity norm of y. I would like to make a note that that inequality is from Holder inequality. It's from something else. It just its general form is this. Inner product between x and y is less than p norm of x times p's norm of y, where p and q must be satisfying this equation. So it's just you get some inequality that looks like Cauchy-Schwarz, but it's actually just not. The way we prove Holder inequality is different. Okay. Let me come back again. Let me come back to this page again that you use Cauchy-Schwarz, but this has to be induced norm from this inner product. Now we go back to the concept of induced norm. We can prove that induced norm, I previously mentioned that induced norm has already satisfied two properties, homogeneous one and the positiveness. Now I'm going to prove the last one, that the induced norm always satisfies triangle inequality. What I show here is that I give an example of inner product in Rn space, right? So the norm here is for two norm. Now I come back on this page, I would like to mention that this is going to be any induced norm from this inner product. All right. So I'm not making a specific assumption about the choice of norm here, only that it is an induced norm. So norm square is inner product between x and y, x plus y. And now you just expand inner product between xx, yy, right? xy and yx, you get this. Let me jump to this. Let me jump to this one right away. Because if you use a field of real number as a field of this inner product space, we know that these two guys are symmetric. They are equal. So I can get a factor of 2 here. So this is equal. All right. But if the field here is not real number, but instead is complex number, these two guys will be complex conjugate to each other, and its sum is 2 times real part. Okay, but let's just focus on the real number. Okay, next this is a very important step. From this you use Cauchy-Schwarz inequality, and then you get this. You bound this term by 2 times its norm of x times norms of y. So after that, you complete the square, and then we get the triangle inequality. Okay. I would like to end this video by maybe posting a question that if your inner product in the space Rn is not the vanilla inner product, not the conventional one, but if I use this one, y transpose wx, where w is anything positive definiteness matrix, what is the induced norm in this case? Okay, so let's think about it, and then yes, in the next video I will talk about the concept of orthogonality.